This is FE Peer Review, the Flat Earth Peer Review channel. The date is June 18th, 2020. The video in review is titled Another Day, Another Doubter. Video author, Rude Earther. In this video, I review the long-distance observations over water made by Rude Earther and identify strengths and weaknesses in a way in which the observations were conducted. My purpose is to provide constructive criticism that will enable Rude Earther to improve his observations and obtain more useful and accurate data. Rude Earther conducts 3 observations from one point. One observation is of a boat off the shore. The other 2 are of buildings and cranes in Liverpool. He documents observer and target locations reasonably well, in that the video can be paused and the necessary time taken for the viewer to note them. This is Rude Earther's video that we see on the screen. His height is 16 feet. He shows us his location data, and this is information about the boat, including the location of the boat. This is from Google Earth, his observer point, the boat location, and the Liverpool buildings. He seems to think he is documenting weather conditions with respect to refraction, but labors under the misconception that this is solely a factor of air temperature in a single spot. We have here his data regarding air temperature at where he is located, which is 19.1 centigrade. In fact, refraction is a factor of differences in air temperature and consequently air density, with layers of air of different densities causing a lensing effect on light rays passing through them. So Rude Earther needs to be comparing the air temperature inches above the water with air temperature at his eye level. A single temperature reading at eye level only provides a portion of the necessary data. For a fuller explanation of air density and refraction, I refer to Bislin's page on refraction. It can be seen here. walter.bislin.ch, refraction in atmosphere. This page gives the full derivation of how refraction and atmospheric refraction works. It's effectively dependent on 2 factors, the speed of light in a vacuum and the speed of light in the medium, which in our case being atmosphere. Everything else derives from that. No need to go into it any further here. Reviewing the observations themselves first, the boat, 105. To clarify, the boat should not be 40 feet behind the curve. That value is based on 0 refraction and cannot be realistically applied to the vast majority of these types of observations. If Rude Earther believes that refraction does not influence observations such as this, he will need to prove that point first, before using that as a basis for disputing spheroidal Earth model results. Under even standard refraction conditions, at most 30 feet would be hidden. Conditions in this image are far from standard. First, note the light-colored band of water. The clearly defined horizontal stripe here is an indication of looming. You can see the horizontal band I'm referring to in this section here, with a clear break at the bottom. The clearly defined horizontal stripe here is an indication of looming. Another clear indicator of strong refraction effects is the degree of waviness in the image. This will be even more apparent in the Liverpool views. Note the waviness of the image. I'd like to take a moment also to point out what we see of the wind turbines near the boat. This is the Gwynty Moor wind farm. Note that the lower portion of the towers is a wider dark band. This can be most clearly seen on the turbine at the far right. Here's the lower portion, and there's a dark band at the base of the tower. This portion is progressively hidden as the towers recede in the distance. That's more obvious when you look at the row of towers on the left with that dark band almost disappearing completely with the last tower. As the walkway is about 1/3 of the way, also note that the walkway is about 1/3 of the way up the tower. So from the base of this tower on the right to the walkway, you repeat that about 2 more times. It's roughly 1/3 the way up. 1, 2, 3. But as the towers recede, we clearly see that they are disappearing from the bottom up, as only the lower portion is being hidden. Note that the height from the horizon to the walkway is now only about 1/4 of the tower height. So here we have the farthest distant tower. We have the height from the base or the horizon to the walkway. We can repeat that approximately 3 times. So this base is now only 1/4 of the height of the total tower, and the dark portion that is at the bottom of it, very little of that can be seen. My suggestion to root earther is to return to this same spot on 10 to 15 occasions on different days at different times of day, and repeating this observation, making special note of the wind tower bases. Their distinct design would reveal the extent to which varying atmospheric conditions cause more or less refraction. A study including 10 to 15 observations taken from the same spot could yield some very interesting and useful results. Moving on to the Liverpool observations, I will focus on the 2 apartment towers visible at this point. What we are seeing here are the 2 towers near Bath Street in Waterloo, 1 tower and the 2nd tower. In addition, we are seeing an earthen bank in front of them. To see the same in Google Earth, here is the observation point. Here are the apartment towers, 1 here, 1 here, and here is the earthen bank, which separates Waterloo and the marine lake from the Mersey River. A useful distinguishing feature of the towers is the light-colored portion near the top, which we can see here. This gives us a scale by which to measure what we are seeing. If we look at these towers in Google Earth Street View, we see the upper 2 floors are painted white. This portion up here. The white portion represents slightly less than 1/6 of the total height. Here is some other useful data we can obtain about the towers from Google Earth. Google Earth shows the ground elevation at the base of the towers. Ground elevation at the base of the towers, elevation 30 feet, and the roof elevation 166 feet. I'm ignoring the elevator, penthouse, and roof stair as it is not necessary for analyzing the video. The overall tower height then is 136 feet, excluding the penthouse, and the tower base is 30 feet above mean sea level. If we use the white portion as a scale, this has a vertical dimension of 1/6 of the total tower height, or 136 feet divided by 6, which equals roughly 22.67 feet. The distance straight down from the tower base to mean sea level is 30 feet. Using our scale obtained from the white portion of the tower, we get 30-foot distance as 30 over 2267, or 1.32 units on our scale. I will return to the video and I will bring up an image I've created in Photoshop where I show the scale. This image I prepared in Photoshop shows the scale overlain on the video footage. If we compare this side by side, we see the street level at the base of the tower. That would be the street level at the base of the tower. Here's the top of the tower. Here's the white portion. We can repeat that 5 more times to get the total height of the tower. This is the base of the tower, or the street level. And below that, a line indicating mean sea level. As the which would be if you were standing at the street and digging a hole straight down at the street until you got to the depth of 30 feet or mean sea level. That would be down here. Mean sea level at below the street level, and here is the street level, and here is the top of the tower. This is the same horizontal elevation as the water of the Mersey River as it meets the sea. This is mean sea level. But as is readily apparent, whereas mean sea level is up here in this general zone, or in this general zone here at the Mersey River, it is down here at the tower. Something is causing 2 points, both at mean sea level, to appear one above the other in the video. 2 points, the base of the tower, mean sea level below the base of the tower, below the street, and mean sea level as seen at the Mersey River. Something is causing 2 points, both at mean sea level, to appear one above the other in the video. Using our scale, the more distant point appears roughly 30 feet below the near point. The more distant point, the near point. What causes the further point to appear lower? Based on the rules of perspective, we would expect to see things below eye level rising to the horizon, with the more distant objects appearing above those closer to us, such as in this example where the more distant book on the table appears above the closer book. However, in this case, the further object, the point at mean sea level below the tower, appears lower than the point near us, mean sea level at the bank of the Mersey. What could cause this observation, which is contrary to the rules of perspective in Euclidean space, in other words, perspective assuming a flat plane? What could cause this observation to be contrary to that rule? One cause could be Earth curvature. Using the generally accepted radius of the Earth, how much drop would we expect to see from our observation point to the apartment tower? Returning to Google Earth, we will briefly check the distance in question, and towers. $17.95 miles. Let's analyze what we see with the Bislin curve calculator using that distance. With data input for the tower and observer height, assuming standard refraction, we have 87.42 feet hidden. However, refraction is clearly far stronger than average when you look at the waviness in the video. This is to be expected as we saw the extreme refraction when looking at the boat and wind turbines. Adjusting the refraction setting in the calculator to 0.57 or strong, 0.57, we find that only 31.5 feet of the building would be hidden. This is approximately what appears to be hidden in the video. This level of refraction, though high, is well within the norms of what can occur naturally. In conclusion, there is nothing in this observation that contradicts the spheroidal Earth model when taking atmospheric refraction into account. As with the wind turbines and boat observation, I suggest to rude earther that he consider doing 10 to 15 sets of observations on different days at different times and documenting as best as he is able the weather conditions. Then comparing these observations to each other to see how much variability there is between them. From this, he will be able to develop a sense of to what extent refraction is influencing the results. I would also encourage rude earther to do an analysis similar to what I've done here using the Bislin curve calculator and considering refraction, as this is going to be the way in which his observations are peer-reviewed by others, including myself. By doing this analysis himself in advance, he will have a better idea what response to expect from the larger community outside of those who already accept the flat Earth model. If you found this video useful and interesting, please take a moment to subscribe and like. Comments are always very welcome, but I request that you keep them polite, avoid ad hominems and insults, and on topic. The topic in this case being long-distance observations and refraction effects. I will be addressing other flat Earth related topics in other videos. Thanks.